Radiation protection in cobalt machine. I am Sanjay Varman, medical physicist, MP MMCC, Varanasi. What is radiation? Radiation basically is the emission or transmission of energy in the form of wave or particles through space. Um, Today my topic is radiation protection cobalt machine. So we have to know about cobalt 60 machine. This machine basically contain a radioactive source which is cobalt 60, and it is also a radioactive material, and that's why from this source gamma rays are produced, and these gamma rays are used for treatment purpose. Obviously it is a external beam radiotherapy. This is Bhavatron 2 machine. This machine in our hospital, Tata Memorial Hospital Varanasi, Government of India. It is Indian product machine. Bhavatron 2 tau cobalt 60 telethery unit, and it is some features of this machine. You are seeing that the first indigenous telecom machine designed and developed by DAE, Department of Atomic Energy, and BARC. And there are a lot of features, especially designed for rural areas. It is power backup 8 hours, majority of motion are computer controlled, facility 0 by 0 field size and asymmetric, jaws differs this machine from other imported machines, etc. etc. And shielding valve composed of tungsten alloy, carbon fiber couch top. You are also seeing that the source capacity 250 RMM. What is RMM? We all know that, of cobalt 60, and it is also a MLC based machine. Okay, so there is a lot of features of this machine, and it is gamma zone monitor. You have to see this monitor, and reading is 00. I do not recommend or promote any company. So this is T-rod. T-rod, why use T-rod? Basically when in a cobalt 60 machine source when stuck, then we have to push by this T-rod to back up the source into the off position or parking position. So T-rod is the very vital, and for safety purpose it is mandatory. It is radiation symbol. It is called trefoil. Trefoil. Features of cobalt 60. Cobalt 60 machines. We have known about this machine, and we have to know also cobalt 60 source. It is high energy, high specific activity, relatively long half life, large specific air karma rate constant, must be available in large quantities. So what is energy of cobalt 60? Average energy 1.25 MeV. From cobalt 60 we get two gamma radiation. One is of energy 1.33 MeV and another is 1.17 MeV. High specific activity 200 curie per gram, and half-life, long half-life 5.27 years. Large specific air karma rate constant. Okay, this is equation, and this equation indicate the how cobalt 60 source produced in a nuclear reactor. System of radiological protection. ICRP has recommended a system of protection based on following principle. These three principles are justification, optimization, and dose limitation. So, what is normal exposure? It is virtually certain that some radiation exposure will result from a normal work practice there, and that the magnitudes are predictable. Potential exposure, not all exposure occur as forecast. There may be accidental exposure. Uh, Basically, unexpected unexpected radiation exposures are termed as potential exposure. Those do not apply directly to the potential exposure. Types of exposure: occupational exposure, medical exposure, and public exposure. It is uh, it is defined by the ICRP 107. So, as per ICRP 107, type of exposure, three types: occupational exposure, medical exposure, and public exposure. Fundamental of radiological protection. The new single approach encompasses three exposure situations: planned exposure situation, emergency exposure situation, existing exposure situations. And there is definition of planned exposure situation, emergency exposure situation, and existing exposure situations. Protection quantities. There linear energy transfer. What is linear energy transfer? Average energy deposited in an absorber per unit distance in KE by centimeter. And stopping power, ability of an absorber to remove energy from a beam of charged particle. Average energy lost by charged particle per unit distance in keV by centimeter. Delta ray contribution is included in stopping power, but in LET, delta rays and Bremsstrahlung contribution is excluded. It is the difference between LET and stopping power. So, what is basic difference between LET and stopping power? In LET, linear energy transfer, delta rays and Bremsstrahlung contribution are not included in LET, but in stopping power, delta ray contribution is included in stopping power. Quantities and units. The quantities for radiological protection remain unchanged, but the radiation and tissue weighting factor used in the calculation of tissue quantities have been revised. Revised WR values are as follows: WR radiation weighting factor, radiation factor for protons decreased from 5 to 2 as per ICRP 103 International Commission on Radiation Protection. Charged particle pions have the same value. WR for neutrons is a continuous function instead of a step function in ICRP publication 60. As per ICRP 60, the WR value was a step function, but as per ICRP 103, it is continuous, which varies as per energy. Okay. And radiation weighting factor for photons 1, electron muons 2, etc. etc. Tissue weighting factors have again been changed and extended to a wider range of organs. This is tissue weighting factor. You are also seeing that. Tissue weighting factor. Absorbed dose. There are a lot of difference definition about this. Okay. So equivalent dose. What is equivalent dose? Biological damage caused by the radiation depends on the nature of radiation, their specific ionization, and LET. Biological damage produced by the same dose of different radiation may be different. Equivalent dose accounts for the different biological effectiveness of different types of radiation. The radiation dose in tissue T is given by the expression equivalent dose ST summation over WR DTR, where DTR is the absorbed dose averaged over the tissue or organ T due to radiation. Effective dose. Radiosensitivity of different tissues in human body is different. So effect of radiation exposure of individual tissues contributes differently to the total health of the exposed person depending upon the seriousness of the damage in individual tissues and its treatability. So effective dose. What is effective dose? So radiation effectiveness do not depends only types of radiation but also depends on types of organ of human body. So this is mathematical definition. E equals to summation over WT HT. HT is the equivalent dose in tissue or organ T, and WT is the weighting factor for tissue T. Tissue weighting factor. WT represents the relative contribution of each organ or tissue T to the total risk due to stochastic effects resulting from uniform irradiation of the whole body. WT values are useful for converting equivalent dose received by one or more tissues in partial body irradiation to effective dose, which is whole body exposure equivalent. And this table for tissue weighting factor, and you are all seeing that as per ICRP 16, ICRP 103, we have given some organs. Radiation effects, two basic types. Number one, stochastic and deterministic. Stochastic, probability of effects related to dose. Stochastic and deterministic, threshold for effect below no effect. Threshold value for deterministic effect, there is threshold value. Below this threshold value, there is no effect. Radiation sickness, CNS syndrome. And for stochastic effect, like gene mutation, okay, this is curve of stochastic effect. This is curve for deterministic effect, and you have seen that there is some threshold value. Deterministic effect, a whole body irradiation. For low LET radiation, there is some immediate effect of deterministic effects. There is dose range and immediate effect with respect to this dose. Local radiation, low LET radiation, dose range and region. In which region radiation incident and effect. What is effect? Safety features and work practice in beam therapy. Planning, area, control panel, signal, door, warning signal, ventilator, exhaust, conduits, etc. It's very important. Risk of radiation. In radiation work, there is risks, some risk. Acute radiation syndrome, possibly death at very high doses. Increased probability of cancer incidence in the exposed individual, hereditary defects in the progeny. Hence, it is necessary to develop safety standards for radiation work so that the risks are minimized. Radiation protection in external beam radiotherapy. The success of radiotherapy treatment is the joint responsibility of the radiation oncology team, which comprises professionals from various disciplines such as radiation oncology, medical physics, medical dosimetry, and X-ray treatment technology are all radiation workers. Equipment design, safety in treatment delivery equipment design. As per IAEA, International Atomic Energy Agency, recommended that number one, failure of a single component of the system is promptly detectable so that any unplanned medical exposure of patient is minimized. The incidence of human error in the delivery of unplanned medical exposure is minimized. The International Electrotechnical Commission IEC has introduced standards to ensure the electrical, mechanical, fire and environmental safety of radiotherapy equipment. So IEC International Electrotechnical Commission introduced some standard for which electrical, mechanical, fire and environmental of any radiation machine. High energy radiotherapy equipment must be provided with two independent fail-safe systems for terminating the exposure, safety interlocks or other means to prevent any unauthorized use. Aims of radiological protection. Aims of radiological protection ICRP 60: prevent detrimental deterministic effects, limit the total probability of stochastic effects to acceptable levels, ensure that practices involving exposure to radiation are justified. Radiation protection. This depends on time, distance, and shielding. The exposure from source at a point will be directly proportional to the time for a given distance and shielding. Distance. The exposure from a source of X-ray gamma ray at a point varies inversely as the square of distance of the point from the source. Shielding. When maximum distance and minimum time do not ensure an acceptably low radiation dose, adequate shielding must be provided so that the radiation beam will be sufficiently attenuated. Head leakage. This is the head of the Cobalt 60 machine. What is the purpose of radiation shielding? The purpose of radiation shielding is to limit radiation exposure to members of the public and worker to an acceptable level. Controlled area. These areas are controls which are under supervision of RSO, Radiological Safety Officer. Uncontrolled area other than the controlled area such as office, restroom, examination room, and control room. These are control console, treatment room, etc. Control room and other than are uncontrolled rooms. Shielding design goal of permissible limit for the area occupied by the worker. Radiation worker 20 millisievert per year equals to 2000 mR per 50 week, 40 mR per week, and member of public 1 millisievert per year, that is 2 mR per week. Barriers. Protective barriers and primary basically protective barriers, and this is primary barrier and secondary barrier. What is primary barrier? This primary barrier is the wall, ceiling, floor, etc. that will intercept radiation emitted directly. So primary barrier is this barrier are facing direct radiation, okay, and secondary barrier which are do not facing any direct radiation, they are facing scattering radiation, leakage radiation, okay. This type of radiation which wall or barrier facing, this is called radiation secondary barrier. So secondary radiation source in external beam radiotherapy leakage depend on design, typically limited to 0.1% of the primary beam. Originates from target, not necessarily via the isocenter. Scattered radiation from the patient, scattered leakage radiation from the walls. Difficult to calculate, use largest field size for measurement. The lower the radiation energy, more of concern for photon beams. So radiation protection survey, head leakage in source of position, it is for Cobalt 60 machine. You can see the value, and this is this, okay. Some accidents in external beam therapy, source stuck, wrong NDW value, and improper use of correction factors, etc. Human error, incorrect use of chamber. Prevention of accident in Cobalt 60 machine. Training, regular quality assurance, QA program, record keeping, education training, careful observation of patient for unusual and unexpected symptoms, etc. Patient identification and chart, etc. Thank you so much.